Let's run through a proof that shows that the limit as theta approaches 0 of sine theta over theta equals 1. Our proof is going to rely on the Sandwich Theorem. And there are two parts to the hypothesis of the Sandwich Theorem. First, you must have an inequality with three functions where the function you're interested in is trapped between two other functions. In this case, our f of x is trapped between g of x as a lower bound and h of x as an upper bound. And then the other requirement for the hypothesis is that you can compute the limit as x approaches c of g of x, and you can compute the limit as x approaches c of h of x, and both of those are the same. They equal this number L. And if that's the case, if you meet both requirements of the hypothesis, then you can say that the limit as x approaches c of f of x is also L. And that's what we're going to do. To do this, we're going to construct our inequality using geometry. Before we make our construction, I want to remind you about the unit circle and where you can find values, trig values on the unit circle. Most people are used to finding cosine theta and sine theta as the x and y coordinates of a point on the unit circle. But this picture shows us that we can find all 6 trig functions in terms of the unit circle. And we're going to use this fact in a minute. So keep this in mind, keep this picture handy, and we'll come back to it. Now let's start our construction. So consider this picture. This is also a unit circle with a radius of 1. And I want you to notice that if we focus on 3 of the shapes here, triangle OAB, sector OAB, and triangle OAD, I think you'll agree that the area of the red triangle, triangle OAB, is less than the sector OAB, which looks like a piece of pizza. It includes this little area here, so it must be bigger. And both of those are smaller than the large triangle OAD. We're going to use that fact to build our inequality for the hypothesis of the Sandwich Theorem. So the gist of what I'm saying here is that I submit to you that the area of triangle OAB is less than or equal to the area of the sector OAB, which is a little bit bigger, and that's less than the area of triangle OAD. That's what I'm getting at. And we can use this unit circle with all the trig measurements on it to write out the expressions for those areas. For the red triangle, we're going to use the formula for the area of a triangle, which is 1/2 base times height. So that'd be 1/2 times the base, which is the radius of the circle, which is 1, times the height, which is this guy right here, BC. And BC, you'll see from our picture here, is sine of theta. And that area is less than or equal to the area of the sector. And the area of a sector is 1/2 times the radius, which is 1, times the angle, which is theta. Not everybody has that one memorized, but you can look it up and verify that I'm right. And that's going to be less than or equal to the area of that blue triangle, which is 1/2 times the base, which is also 1, times the height, which is this orange guy over here, which is tangent theta. That's supposed to be a tangent there. And so if we clean this up a little bit, we get this inequality. 1/2 sine theta is less than or equal to, oops, I don't know what that is. Let's get rid of that. I hit the wrong button. Less than or equal to theta over 2. And that's less than or equal to 1/2 tangent theta. So the first thing I'll do is I'll multiply everything by 2 to get rid of those fractions. I'll start that on the next screen, and then we'll see that we have an inequality that we can work with here. So we have this inequality. Let's eliminate the 2's. We'll just multiply the whole, or the 1/2, the halves. We'll multiply everything by 2, and you'll agree, I think, that we end up with sine theta is less than or equal to theta, which is less than or equal to tangent theta. And I'm actually going to write that as sine theta over theta. Cosine theta. Okay. So this is true. Now, our problem is we don't really want theta in the middle. We want sine theta over theta in the middle. That's the thing that we're trying to find the limit of. But I can't just go and throw a sine theta on top. Math doesn't work that way. What I can do is I can divide everything by sine theta. So I am going to go ahead and divide each of these by sine theta. And when I do that, down here on the left, I get 1. In the middle, I get theta over sine theta, which is kind of like what I want. And here I get 1 over cosine theta because the sine theta is canceled. Now, what I need to do is I need to do what we call the old switcheroo here. I need to flip this whole thing over so I get sine theta over theta. Just remember, when you do that, you have to flip the inequalities. Let me show you what I mean. 1/2 is greater than 1/3. But when you flip these over, this becomes a 2 and this becomes a 3. And in order for this thing to still be true, we have to flip these over, right? So if I'm going to flip all these inequalities over, I have to also flip the signs. So I'm going to say 1, the reciprocal of 1 is still 1. I'll flip this one over. I'll make this sine theta over theta. And I'll flip 1 over cosine over, and I'll get cosine theta. Okay. And just for clarity, let's go ahead and write this in the familiar direction, which is cosine theta is less than or equal to sine theta over theta, which is less than or equal to 1. Okay, so we're almost there. Now we have part of the hypothesis, and I'm ready to finish this thing off. We know that sine theta over theta is trapped between cosine theta and 1. And these limits are easy to calculate. The limit as theta approaches 0 of cosine theta can be found with substitution, and that equals 1. The limit as theta approaches 0 of 1 is a constant function, so that's a 1. And therefore, since both of those are 1, the limit as theta approaches 0 of the middle thing, which is sine theta over theta, must also equal 1 by the Sandwich Theorem. And we've proven what we set out to prove, which is that this statement is true. And we had to use the Sandwich Theorem to do it. Took us a while, but I hope you'll agree that this is kind of an elegant proof, and it was fun for me to do. Good luck with your math.